I want to talk about another way that we can solve recursion in lattice. Right, so the problem was that we had a function defined in terms of itself, and so we couldn't create a closure that contained an environment that contains a closure that contains the environment that contains a closure, etc. But what we can do instead is break up the function into two functions which call each other. This is typically called a Y combinator. This is not going to be in the syllabus, so you're not going to be tested on it, but you should know what a Y combinator is if you've gone through a programming language course. So we're going to give a little talk about it, right? So in the abstract world, right, a Y combinator is a function Y that you feed a function F, and it gives you back F applied to Y of F, which then, of course, if you realize what Y of F is, that's going to be F applied to Y of F. Which, one more parentheses, which, right, we can resolve that inner part, and that's going to give us another F on the outside. And we can keep on doing this until our recursion tree is exhausted, right? Each one of these F's could be taking in a slightly different parameter as we go down. So for instance, let me do an example of factorial in this format in our let, right? So we'll have let almost fac. This is going to be a function that takes in a function, right? So maybe let's call that next function. And what should it do? It's going to return a function that takes in an x. And if, right, this is going to be essentially the state where we do our factorial, right? If x is less than or equal to 1, then we're going to return 1. Else, we want to return x times next func. Right, next func should take in another function, which will pass in next func again. Right, this is the tricky part. And then we'll apply that on x minus 1. So this isn't quite factorial because, right, it has the factorial base case and sort of the return value that we want, but we're no longer calling factorial on itself, right? We have almost fact here, and we're getting a function's name here, and we're applying that function maybe with itself, right? And then we're going to, so this will all be in, let factorial, our actual factorial, this is going to be a function that takes in an x. And what does it do? It calls almost fact on almost fact of x. And then we can actually call it, right, in factorial of, say, 5. Okay, let's see what we did here. Right, so when I call factorial of 5, what happens? It's a function that takes in 5, and then we're going to call almost fact on almost fact of x. Right, so almost fact is up here, and we're passing in almost fact as the next function, and x as this value. So we're going to get 5 here. We check, oh, 5 is not less than or equal to 1, so we go to this else statement, and we say x, right, 5 times, well, what is next func? It's almost fact again, right? Somehow we got to a recursive definition, but why does this work, right? So then we're calling almost fact on almost fact again at x minus 1. Pretty tricky, right? So what's going on here? Well, almost fact, when we have this placeholder function, this is a well-defined, right? Because this is just some value. We're hoping it's a closure. We're assuming it's a closure, right, that we're passing to our function. And so this is totally fine and in the environment of the body of our function, right? Because this is what's going to be bound when we end up doing the call to almost fact, is we're going to bind whatever this function is to this name new next funct. And it's able to, right, next func is well defined in here, and so is next func again. and x minus well defined. So this is all well defined and in the environment of the closure of almost fact. And then down here, right, when we call define fact, all fact has already been defined, right? It's in the environment of this closure, right? Because it's been defined before we define this one, so everything that's been defined before we define this function is captured in the closure's environment. So almost fact is a perfectly good function to add into our environment. And we can obviously call it twice or call it on itself, and that's totally fine. And this is the way that you get around having to deal with full-on recursion, right? I like our let rec form because it lets you naturally define recursion as opposed to having to, every time you want to do recursion, you need to think about how am I going to modify this, right? How am I going to make this y combinator so that when I pass in yf, that's this almost fact with x, right? It's going to pass itself in, right? So the f function is this multiplying by x, and we have the yf again, which is next func, actually almost fact, right? And so we end up with the structure, but you have to you either have to like come up with the generic y or roll your own every time, and it's just a bit of a pain. So hopefully next time you hear Y Combinator, you won't think about Silicon Valley as much as how do you get around recursion, right? By having two people speaking at each other. It's maybe a nice way to think of it. Cool.